Hello YouTube, this is my first video. My name is Phil Nye, the physics guy, and today I'm going to be talking about Pikes Peak. Now this is an observation which has been passed around in the flat earth community as a proof that the earth cannot be a sphere. And the point of my presentation today is to present a ray tracing model using actual elevation data to show that this observation is not only perfectly possible on a spherical Earth, but impossible on a flat Earth. Now, in order to actually do this, we need to get data for the elevation profile in order to actually do this simulation of the ray tracing and then get the rendered image of what we'd expect to see on both a flat Earth and a spherical Earth. Now, the data that I'm using here is provided by the Shuttle Radar Topography mission, one of the later ones, which had a 1 arc-second resolution. And the data you can download via the earthexplorer.usgs.gov, free of charge. You just have to sign up with a username and account. And here I show the area for which I calculate or I downloaded the data for, and it's almost half of Colorado, which is where this observation was taken. And here are the GPS coordinates of the 4 corners, and you can use that to get the elevation data. Now, it's worth noting that this is the same, at least part of the data set that is used by Google Earth in order to show the topography and the terrain like they do in their 3-dimensional models, which is kind of interesting. So basically, we'll have an accuracy similar to that of Google Earth, which for any of you who have actually used Google Earth know that it's not perfectly accurate, but it's going to be good enough. And especially for mountains and stuff, the plus or minus 30 meters error bar is going to be negligible because these mountains are going to be thousands of meters tall. Now, just to show you that the data that I'm using is actually from Google Earth, we will actually take some data from Google Earth and compare it to the data that I've generated by my own model. And so here I show the observation location, the GPS coordinates, and the location of Pikes Peak. You can take these and plug them into Google Earth and draw a straight line, and you'll see something very similar to this image that I show here. And I've taken that line and I've gotten the elevation profile. And so I want you to pay attention specifically to the various details. So there's this gradual decrease followed by 3 hills and then a valley, and then there's another segment of 4 or 5 hills, and then it goes into this jagged sawtooth peak, which then goes down and then back up to the top of Pikes Peak. So this is the features that we're going to use to compare to my elevation data. And here's what I get by taking the topography data and doing what is called a linear interpolation between those points. I will not go into the details about this calculation that I did to get this particular side view here. That will be left to a later hangout with the Rumpus and others, where we talk about not only how you can generate a curve like this using my refraction software, but how you can then take this and render 3-dimensional scenes with refraction, which is very powerful, especially for people who are trying to figure out what the shape of the Earth is. And let's just go through. I feel the need to go through and show you guys that all the features match. So there's the dip, and there's the 3 bumps, and then there's the dip again, then there's the 5 bumps, which go into this jagged increase, which then goes into the decrease, which then goes up to Pikes Peak. And this is over a 225 kilometer distance. So funny enough, this is exactly what I'm going to be using to simulate both the flat Earth and the round Earth. Now, when I take this data and put it on a round Earth, I need to take into account the drop. Now, this is the whole crux of the issue. So flat Earthers are saying that this drop is not there in the picture. I'm going to say that it is most definitely there. In fact, it is so much there that this observation would be absolutely absurd on a flat Earth, and I'm going to actually show that this observation is absurd on a flat Earth. Now, you can double check that I'm using the correct curvature of the Earth by looking at the side here. You see that this is at 0, right? And so all my elevation is going to be measured to the observer location at 0 kilometers. And if you look at the Earth curve calculators and you look at the a distance of 225 kilometers, you should see that the drop value is close to 4,000 meters. And sure enough, if I look, I have a parabola here, right? Parabola, 8 inches per mile squared. The parabola starts out at 0 with a slight amount of curvature, and then we have the cumulative curvature drop, which flat earthers like to point out, the 8 inches per mile squared, which then goes down to about 4,000 when we reach a distance of 225 kilometers. And if you do the actual calculation, you'll see that it matches exactly with the curvature calculator. Now, I mentioned in the very beginning that I'm using a ray tracing model, so let's just quickly go over what a ray tracing model actually is. Now, you might have heard about this if you're into gaming and stuff. It's a very high-end way of rendering very, very interesting optical effects like reflections and refraction and stuff like that. So what is ray tracing? Well, ray tracing specifically is a method to take a 3D digital model, a model in 3-dimensional space, and map it to a 2-dimensional image. Now, it's done in such a way that it's supposed to preserve perspective. And again, sorry for the noise. There is trucks going outside my apartment. So anyways, these rays are actually meant to represent the light that is coming into the camera. Now, why is it that the light that I'm simulating is coming out of the camera instead of going in? Well, it turns out that you can actually, because the light is actually a reversible process, meaning I can take time and if I flip the direction of time and go backwards, the trajectory of all those light rays will actually go in the opposite direction, as if the light was emanating from the camera. This is a physical symmetry that's involved in the equations and that describe light. And so instead of having to simulate all of the scattering of light off of the objects, it's much simpler to take the light and reverse it and see where the light actually goes into the scene. Because those rays which go into the camera are going to be the same rays which would be going out of the camera. Now, in this case, I'm representing each ray, each light ray, as a pixel in the image. And you can think about that as a photon which is coming in and hitting the sensor on a particular pixel. And that photon determines the color of the image. So basically, wherever this ray hits in the scene, it will determine the color which the pixel gets when you render the image. Now, the nice thing about this method is it allows you to do fairly complex calculations in terms of reflections and shadows and stuff like that. Now, my ray tracer does not do any of those things, does not calculate reflections and shadows. However, it does calculate perspective. And we know that it calculates perspective for the following reason. As you move farther away from the camera, the number of rays that you get per unit area decreases, right? And you can even see this in the image. The rays spread out in the direction that the camera is pointing. Now that means that as an object moves into the distance, the number of rays which actually strike the object decreases, right? And so when I render the image, an object which is farther away will have less rays that hit it. And you can actually then take that and use it to calculate the angular size. So if I take this image here and I calculate the number of pixels that the object takes up in this image compared to the field of view of the camera and the number of pixels total in the image, I can then calculate the angular size. And if you do this calculation, you can show that this method actually reproduces the exact angular size that you would expect to see with an object in the distance. And this is what you see in the rendering. So as the object moves farther away in the orthographic projection, the size of the object in terms of the frame gets smaller, right? And it gets smaller according to perspective. Now, another neat thing about this ray tracer is that you can actually calculate things like refraction. And what that allows you to do is that instead of having these rays go out in straight lines, you can actually calculate the curvature or the bendiness of these rays according to the atmosphere. And this will actually be very important for this calculation because we're not just going through, 1 kilometer of atmosphere, we're going through 200 kilometers of the atmosphere. So foreshadowing here, refraction is going to be important. But let's just discuss the case with no refraction and see where it leads us. So here is a side profile view of the camera rays emanating out from the camera and showing where they hit in the elevation profile that we derived earlier from the USGS data. As you can see, most of the field of view is taken up by the sky, and then some of the field of view is taken up by the land here. The green rays represent where the rays actually hit. And so you can see then that there are 3 rays which just peek over this hill here and go all the way to Pikes Peak. Now, when I do the actual rendering, I'm going to do a larger density of rays, which means that I'll get a much higher resolution image. And so there won't be just 3 pixels. It's actually going to be a much more significant fraction. But you can see that I can just barely see the top of Pikes Peak. And so when I take this ray calculation and then I use it to render an image, I see something like this. Now here, this orange color up here is the color of the sky, and as I go farther and farther away, the ground fades more and more into the sky color. So you can kind of see here that black is very close, and then it gets a little bit closer to orange, and then even closer to orange there. And then eventually you see this little peak here. And this is exactly Pikes Peak, just poking up above the bumpy horizon. And you see that it's a much lighter color, right? This represents the fact that Pikes Peak is 200 kilometers away. Now, we can see Pikes Peak, but we don't see a lot of it, right? And that's because we do not have the atmosphere, right? So in order to actually make a realistic render of our scene, we actually need to take into account all of the effects that are in play, right? So in this case, the atmosphere is in play because we live on a sphere which has an atmosphere, and that atmosphere is non-uniform. It has all sorts of varying density gradients based on the weather and also as you go up in elevation, right? So if I go up, we're up a mile above sea level, and so the atmosphere is much thinner than it is at sea level, right? If anyone has been to Colorado or been up in the mountains, you'll see that the atmosphere gets thinner. You'll experience it in terms of not being able to breathe well, unless you live there, of course. Anyways, there is a way of simulating the atmosphere, simulating the major effects that we see. So, for example, this density gradient as a function of elevation. In the simulation, the approximation that I'm going to be using is what is called the International Standard Atmosphere. And you can Google this thing, and there's a nice Wikipedia article, and it tells you about how the International Standard Atmosphere works and how it is solved. Basically, it involves solving a first-order differential equation. So for any of you who've taken calculus, you should understand what that means. And it's also a separable equation, so you can actually solve it fairly trivially. Now, in my particular model, I'm not solving it with pen and paper. I'm solving it using a computer. So you can actually solve it not analytically, numerically, using a numerical integrator. The same thing I'm using to solve the rays, by the way. And there's one particular approximation that this standard atmosphere does. It makes the approximation that the atmosphere is uniform over the surface of the Earth. Meaning that if I look at 2 points on the surface, they will have the same temperature, but then if I increase in elevation, right, then the temperature will change and the density will change and the pressure will change. All of the variables will change, but they'll be lockstep with one another. Now, this is a very simple model of the atmosphere. I will admit that it's very simple, but it actually does a pretty decent job in most cases. And my software not only allows to simulate this very simple approximation, but we can also add in effects where you have a non-uniform atmosphere over a particular path. But in this case, we'll keep it simple. We'll use an approximation of the atmosphere, which as I will show you, is a really good approximation for the atmosphere. Now, this model of the atmosphere only gives me the density of the air. It does not give me the refractive index. But it's actually, once you know the density, it's actually very simple to calculate the refractive index of the air. And I basically follow exactly what was done in this Gutierrez paper, Computer and Graphics, Journal 30, 2006. If you Google this, you can download a copy for free, and they discuss, basically, they discuss all aspects of modeling atmospheric refraction. And it's a very complete article. They actually talk about how to simulate refraction using Fermat's principle, which is the same thing that I'm using. They show you how to derive expressions for the atmospheric conditions. They show models for various types of miraging, like inferior, superior, or fata morganas. It's actually quite a good article. I would recommend going through if you're interested in understanding the mathematics behind refraction and miraging. Now, of course, my software uses a very similar principle, but it's written in such a way that it's hopefully simple for the user to use. I'm going to have a hangout with the Rumpus in the near future, maybe a little bit farther, depending on how busy everybody is, and we'll talk about some simulations using this ray tracer and comparing them to real life observations, just kind of like in this video here. And then hopefully we'll have a hangout where we talk about how to use this refraction simulator. And it will be completely hands-on. There'll be some sort of basic Python that you'll need to know ahead of time, but it's actually fairly straightforward to use. You can kind of get a feel for it just by looking at the code that I write for these sorts of calculations. All right, so after doing all of that, getting the atmospheric model, calculating the index of refraction, calculating the trajectory of the light rays using Fermat's principle, we get this result here, this beautiful diagram which shows us the trajectory of the rays. Now, what you'll notice is these rays are definitely not straight, right? They definitely move and they curve. But look at how far we've gone. We've gone over 200 kilometers, and the rays have dropped maybe 500 meters. Yeah, it's not very much. So 500 meters over a distance of 200,000 meters. That's very tiny amounts of refraction. And so I know that I'm going to get flat earthers who say, oh, look at how much refraction they're adding in. Oh, it's ridiculous. Oh my God, that's not what we see. It's really not that much, guys. Like I said, you go, yeah, roughly 500 meters over 200,000 meters. Like, that's nothing. Like, that's absolutely tiny. But it works. So here, instead of seeing just a few rays hitting the peak, we actually see a significant number of rays hitting the peak. I don't know if I discussed this orange ray, but basically this orange ray is eye level. So this would be pointing to where a theodolite or an autolevel would look relative to the scene. So the theodolite would show an eye level which is roughly above Pikes Peak, because again, everything's dropping away from you because of the curvature of the Earth. So this is one way of actually verifying this observation is dealing with curvature. But in this case, I'm just going to literally just show you side-by-side comparison. What does the 3D model show? What does reality show you? And I'll let you guys be the judge on what you think is actually happening. So here are the results. This was a total of 2 minutes on the computer, which I think is great. It really doesn't take very long to do these atmospheric calculations, thankfully. So yeah, much more of the peak is shown. In fact, we actually see not only just the Pikes Peak, but we also see these mountains on the side, which is very nice. So let's crop this down and let's compare it to the actual observation. Now, it's not exactly scaled correctly, but I just want you guys to focus on the percentage of the frame in which this, or the percentage of how much there is a Pikes Peak versus this side peak. And I mean, guys, look at it. Like, it's pretty damn close to matching, if you ask me. I didn't overlay them. I didn't do all this other stuff. It's not really that important. I mean, I've basically done my due diligence. I've shown that you can see Pikes Peak on the spherical Earth. And not only have I shown that you can see it, but it looks almost identical to what we see in reality. So that's pretty cool. So let's look at the flat Earth. And of course, this is going to be a fail because we know that, guys, I know this is hard, but the Earth is not flat. Sorry. Yeah, so this is the same field of view camera as before, but you can see how much green there is. Look at all that green. Look at all that land that's taking up the frame. It's taking up almost the entire frame. And it's very simple. This is, I mean, there's no drop, and so therefore we should be able to see all of this mountain right here. Like, this should be visible. And I've even included the atmosphere. So the atmosphere doesn't really seem to help. It actually hurts the flat Earth because, again, principle is light rays moving from a more dense atmosphere into a less dense atmosphere means that light rays will get bent down towards the more dense atmosphere. And so what this means is that all of these light rays which are going out just get bent down towards the surface of the Earth, basically allowing us to see beyond a mountain, like right here, which is kind of silly. Yeah, I mean, the whole thing is silly. Like, the Earth is definitely not flat. But let's just give it a chance, guys. Maybe something will happen once I do the three-dimensional render. Not really. Yeah. I mean, basically this feature here, right, that we see this almost flat kind of mountain range here going through the center of the frame, and then here's all of those hills below. I mean, it's worth noting here that I had to tilt the camera up by almost half a degree in order to even get this mountain in frame. So with the same field of view as the spherical Earth, you know, the mountain doesn't even fit in the entire frame unless I tilt it up. And so I'm actually missing the land below. I mean, it's just, yeah, I mean, that's basically it. So flat Earth gives completely absurd predictions for what we should see. The spherical Earth gives very reasonable predictions for what we should see, and those predictions actually match our observation. Now, people can be pedantic and say that it's not spherical, but I can tell you that this 100% shows that the Earth is not flat. Like, all of this mountain here basically shows us that there is a drop, and that drop is visible when we look into the distance. All right, that's all I got, guys. Thank you so much for tuning in. And please let the right people know about this calculation. Let's start a little debate about this. All right, thanks, guys. Bye.